Hey you, wanna see something cool? Here we have two materials, material A and material B. What if I told you that material A is one of the keys of the technology development we have today? Don't believe me? Well, let's begin with the weight. We will put the two materials in a weight balance to see which one is heavier. As you can see, material A is way lighter than material B. Now, what about the strength? Of course we don't want our things to break. So let's begin with material A. We're going to hit it hard with anything, like a ball. Did you see what happened? It just bounced away. And now, material B. Oh, it looks like it got a crack due to the impact. This means that its strength is not as high as A. One thing that engineers, designers, and companies consider is a balance between the strength and how much energy it can resist. This is called toughness. To understand this, look at this example from a plane, in which its right wing is made from material A and its left wing from material B. When we apply air forces and pressure from below, we can see how wing A bends and goes back to its position. And if we look at wing B, it breaks. This tells us that material A can absorb more energy than B. Let's don't forget that there are also environmental conditions that affect the materials. For example, rain. Wear can highly affect the objects due to corrosion after we expose them a long period of time. Let's see how they react. We can see that after some time material A is as good as new, but material B is starting to corrode, which causes problems in its strength and also a shorter life. So, what have we learned so far? That this material has less weight than the others, also that its strength and toughness is pretty good, and finally that it doesn't corrode with environmental conditions. At the end, this means that the products made with material A will perform better and even have a longer product life. This will be reflected in more money. I guess you're wondering by now, what is the material A and why is it so awesome? It's called carbon fiber reinforced polymer, which is a composite, by the way.
So now we know the superior properties of carbon fiber composites. Let us look at the origin of carbon fiber. The earliest known use of carbon fiber was by Thomas Alva Edison in the year 1880. Edison tested various possible materials for the filament of the light bulb, but none of the materials were suitable for the use in light bulb. This is the eureka moment for Edison. One of the materials that Edison tested was carburized bamboo fibers. Edison took bamboo fibers and superheated them to obtain carburized bamboo fiber. He found out that it could withstand high temperatures and was a great conductor of electricity. This filament was successful in lighting the bulb, and Edison filed a patent for electric bulb in 1880. Carbon fiber can't be used as it is and must require some form of consolidation. That's why we mix it with a polymer matrix. Let's take carbon fiber oriented in a particular direction. The carbon fiber can be of many types: high strength, intermediate modulus, high modulus, and ultra high modulus. The selection of the fiber is based on the application. Then we have a polymer matrix, which can be epoxy, which is the most commonly used, and PEEK. Both the fiber and matrix will undergo various treatment processes before obtaining the carbon fiber reinforced polymer. This can be carbon epoxy, carbon PEEK, and many other names depending on the fiber matrix orientation.
Here we can see a unidirectional ply with carbon fibers held together with polymer matrix. If we put it this way along the fibers, it has amazing strength as the fiber is in the same direction as the load, so it can resist it. But if we put it this way, you can see there is no continuous run of carbon fibers to resist the force. As a result, the polymer matrix can be easily pulled apart, and the fibers add very little strength to the composite when the force is not applied in their direction. To solve this, we add laminates with fibers on top of each other. Here we have 0-degree layer on top of 90-degree layers, and 45-degree layer on top of 0 layer, so the properties are the same in those directions. We can also add more layers until we have similar stiffness in all directions. But we should notice that the thickness will become too great if we do so, and we may get delamination of the layers, which we don't want to see.
So, where is CFRP used? They have been widely used in various industries. You can find it in automotive, sports equipment such as golf shafts or skis, aircraft, helicopters, and even some parts in space applications. I think you want to see some examples, so let's begin with planes. One clear example is how much it is used in current aircraft, commercial, light ones, and also fighter ones. This particular one, model Airbus A320, the plane uses a specific composite called carbon fiber epoxy. This is used in the inside of, well, a lot of parts: vertical stabilizer, horizontal stabilizer, brake disc, wing box, internal and external spoilers, and some section of the fuselage. These are just some examples. Of course, it varies depending on the model, but now you have an idea of the extent of the applications. What about helicopters? Well, there are not as many uses in them as airplanes, but still have important roles in their design. For example, the blades are reinforced by carbon epoxy, among other ones, which result not only in important increase of strength, but also increases their safety.
As you can see, this material is extremely useful in the industry, so its usage has increased, but also the amount of waste. As the chart shows, the yield value has increased incredibly in the past 10 years, and the number is predicted to rise to 140,000 tons by 2020, with an end-of-life waste of 62,000 tons. So, how can we deal with such numerous wastes caused by CFRP? Usually, there are three major kinds of methods. The first one is mechanical recycling. During the process, the material is ground in a hammer mill and degraded into different lengths, reducing the size of composite to micrometer levels. The second one is thermal recycling, in which we have two types: pyrolysis and fluidized bed process. Pyrolysis consists in the decomposition of polymers at high temperatures, enabling the recovery of long fibers. Another option, the fluidized bed, consists of a sand bed in a volatile environment with the fluidized air that decomposes the polymer resin and release the fibers by washing them away with the air. The third method is chemical recycling. Chemical recycling process uses a solvent such as water, acid, and alcohol to degrade the resin and recover the carbon fiber. The process is able to recover high-quality carbon fiber with loss of tensile strength and recover the polymetric matrix. Recovered carbon fiber provides opportunities to reduce negative environmental and financial impacts compared with virgin carbon fiber production.
Now hopefully you have learned about this awesome material and all the application it has. Of course, there are more things related to this and we encourage you to read more about it. Thank you for listening and not sleeping throughout the video. These are the group members: David, Fardan, Kang, and Ruiqi. Goodbye.